Good morning. I wish we could be with you in person, and my wife wishes we had our date week in the mountains, perhaps next year. I suppose this picture will have to suffice for the mountains, though. But all the same, thank you for joining us virtually. And while I'm sure you'd rather be in Keystone than in your basement, bedroom, or backyard, the silver lining to all this virtual venues that you'll be able to rewatch this recording many times, and perhaps with family, friends, and loved ones. Now, this presentation is first of a three-part series that focuses on the outcome of collaboration across various entities, including contractors, communities, CTPs, and FEMA. And each presentation that's listed in your agenda is going to speak to a different aspect of this associated with the overall effort, which I'll overview shortly. Since we don't get to connect with you in person, just wanted to share a little bit about each of us. So I'll go first, and then Josh will introduce himself, and we'll kick off our presentation. So my name is Geoff Uhlemann. I just joined Michael Baker in August of this year after 12 years with AECOM. I've got 4 kids, and actually 1 on the way, and happily married for 14 years now. And we love to get out and camp, especially in Utah when we have the time.
Thanks, Jeff. Hi, everyone. My name is Josh Hill. I've been at Wood for 3 years now, and outside of work, my wife and I enjoy getting outside, especially skiing. Back to you, Jeff.
Thanks, Josh. So this slide summarizes the presentation block. So the next 3 presentations, including ours here. And rather than calling it 2D modeling, I think a better title might be 2D collaboration without borders. It is focused on 2D modeling, but different aspects of it. And so the first one, what this presentation is we're calling it 2D technical consistency and recommendations. A lot of that's going to focus on rain-on mesh or applied precip. And then we're going to kind of overview. This will also serve as an introduction to the next 2 presentations. It's all part of one larger effort. The next presentation that you'll hear is going to be on how those products are used and communicated. And then the third one is going to be on the national efforts, which actually originated from the same effort, but went to a national scale where there's a Floodway IPT. And you can see on the right-hand side here, the C2DC is a Colorado 2D consortium. And there's a whole bunch of people mixed in there, and we're kind of a subset, this presentation, for the Rain on Mesh Best Practices Initiative, which I'll overview. Now, as the saying goes, there's no I in team, which is why I turned my video off for this slide. And this really was a team effort. And by team effort, I don't just mean a lot of people involved, but really one person driving it while others give a yay or nay or just review emails. There truly were many people that chimed in, and we were able to draw upon their experience and examples throughout the process. Now, when we all work together, we're each better because of it. When it comes to knowledge sharing, it is not a zero-sum game. We each have more opportunities and better products as a result. Now, admittedly, as being being a contractor, we often hold our cards close to our chest. There can be a tendency to hold back or outmaneuver, try and get the right angle. And I'll admit there's a time and place for that, especially with tools, graphics, strategy, etc. But when it comes to methodology, quality, and the level of detail, it's really helpful to have everybody bring their best to the table and have everybody on the same page. So think of it like a 2D technical modeling potluck, where many of us have worked on similar efforts and programs, but each individual and entity has a different experience and different exposure to specific use cases or maybe unique challenges that arose out of that help them refine their methodology or process in this area. So each of us was able to bring a slightly different perspective. Transparency of our group and this initiative in particular, the Rain on Mesh initiative, was a breath of fresh air. And we shared resources and did trial tests or demos to show the difference in the results of the various approaches. And because of that, everybody wins and advances the science farther. So with that brief background, we come to the subgroup of our focus here, the Rain on Mesh Best Practices Initiative. And the main goal here was consistency among our contractors and teams so that we would have an improved product, methodology, and reviews. And it actually kind of arose out of having the CWCB recompete for the next 5 years. We had 4 contractors selected, so you have AECOM, Baker, Wood, and CDM Smith. And we wanted to make sure that the 4 of us weren't giving 4 different products, 4 different methodologies or techniques to the client. So instead, we formed a group to where we could all collaborate around that. And we wanted to step through a lot of the methodology and make sure that we are on the same page. And so out of that arose this Rain on Mist Best Practices group, which I'll overview a little bit more. Now, a secondary or ancillary benefit to it, but not the primary purpose, is that now we have established some additional resources that can be used for training, both internal within our companies and external for clients, communities, etc. And then also we have some recommendations that we can carry forward to FEMA where there's where the guidance is perhaps lacking. In terms of how our group actually functioned, we kicked off in December 2019, identified all the topics that we wanted to cover, assigned people that would spearhead each of those, and then set up a 12-meeting series that extended into July and then had a report out, kind of final conclusion in August. But we had 26 people participating across 7 different states, and on average we had 21 or 22 people in each meeting, so very consistent involvement, and I would guess maybe 350 some hours spent across this, but it was great to have everybody's perspective and contributions. This slide summarizes the process, how we went through it. So the first thing that we wanted to establish is, why is this topic relevant? What's important about it? Once we had that established, the what and the why behind it, we would each share kind of the common practice that stemmed across the group and agree on items that are best made consistent versus things that are maybe trivial in nature or more process driven, but we wanted to at least share common principles. Once we had that, we'd recommend what the best principle is moving forward, not the process. We want to allow freedom and form, but we wanted to at least be consistent in the function or the implementation of it. And then the goal here at the end was to document it so that we don't forget what we talked about. So we document that in emails and then have a PowerPoint, a master PowerPoint that captures all the main highlights of it. And then also we built a library with additional articles and examples and the detailed agendas that we went through. And this should all be either on the SharePoint site, or if it's not yet, just email me if you want a copy of it. But our end goal here again was to have unity and bliss among everybody, but also training resources as well. This is the last slide kind of overviewing before we jump into actual specifics. So you'll see these are the 9 different topics that we focused on. If you remember, we had 12 meetings, so a few of them like hydrology and 2D floodways and mapping each took 2 sessions. But we stepped through it in a pretty logical sequence in terms of, going from top to bottom on this list shown here is usually the order that you'd proceed in. So we went through each of these topics, and the ones that we're going to briefly touch on, we wouldn't be able to cover all the material even in a couple of hours, but the ones that we'll briefly touch on are the ones that are highlighted in yellow here. And I also want to make a caveat that a lot of our recommendations were centered on HEC-RAS in terms of if we gave an example in a specific process. The principles could stem across really any modeling platform or software, but a lot of our focus again was rain on mesh or applied precip, which usually when you're doing that, it's going to be a larger watershed based, which HEC-RAS is usually a more efficient way to do that. So now Josh is going to kick us off first looking at mesh refinement.
Thanks, Jeff. Yeah, so the first mesh refinement or model refinement topic I'm going to discuss today is actually refinement regions. So the first being channel refinement regions. So what these are delineated along your banks of your channel. That can be seen in the figure on the top left, the kind of dark gray. And what these are meant to do is to not only align the 2D mesh cells in the direction of flow along their channels, but also they're used to align this outside edge of your channel cells to the high points of the bank on either side. And then next we have floodplain refinement regions. And what these are meant to do is to reduce your cell size from your larger cells used for the upper parts of your watershed for just the purely rain on grid portions of your model, and reduce those cell sizes for the kind of more concentrated flow and or floodplain portions of your model. To, not only increase the hydraulic accuracy of your model, but also to help with the mapping rendering side of things as well. And then finally, we have urban refinement regions. So you can either use these to refine entire municipal boundaries of a town or a city, like the figure shown here, or alternatively, you can just refine certain portions of urban areas. But no matter what you choose to do, you can just use these urban refinement regions to help increase the detail or mapping and rendering in certain locations in urban areas. And just a note for both the channel and floodplain refinement regions, you can actually automate the process of this typically for like larger watershed-wide model scales by buffering either flow accumulation grid lines or by using hydro-flattened portions of your DEM. So next I'll discuss break lines. First kind of grouping I'll discuss is going to be your stream bank or stream centerline break lines. And what these are trying to accomplish is something very similar to the channel refinement region. They're trying to align the 2D mesh in the direction of flow along your channel, and also to align the outside edges of your channel cells to the high points of the bank on either side. So this first figure here is showing an example of stream bank break lines. So there's going to be a break line on each side of your channel along the high points of the bank. And these are typically used for your mapped areas or more detailed areas of your model. They're a little bit harder to generate and harder to actually enforce in your model correctly. So alternatively, for unmapped or more approximate areas in your model, you can use something easier, and you can use stream centerline break lines. So you just have one break line along the center of your channel, and you can adjust the cell spacing along that break line so that the outside edges of each of the channel cells on the right and left of the line here align with the high point of the bank on either side. So no matter what, whether you use the stream bank or stream centerline break lines or the channel refinement region, kind of the one thing you need to watch out for, especially in HEC-RAS, is to ensure that your channel cell faces capture your channel Mannington value. Right now, the current version of HEC-RAS assigns your Mannington value for your cell face based on the midpoint of the cell. So you need to make sure that your cell orientation and your cell spacing along these break lines or refinement regions is appropriate, such that your channel cells are picking up that channel Mannington value. So then moving on to kind of roadway or dams or any kind of embankment break lines. There's a ton of sources out there to kind of automate or kind of start generating some initial break lines for these features. However, ultimately you're going to need to review and often manually edit these features to ensure that these break lines are along the highest point of the embankment. Also, just kind of note here too, for overtopping features, a lot of times they can be shown as disjointed for inundation mapping if you don't use appropriate cell spacing. So for any overtopping features, make sure you refine your mesh enough around these features such that there's continuous inundation across any overtopping features. So next we'll talk about approximating structures. So oftentimes for rain on grid models, especially large watershed scale models, it's not in the scope to model each individual hydraulic structure in detail. So there's several ways you can approximate the hydraulics of these structures. Here are the three methodologies that were discussed. I'll start on the left here with the offset break lines. This is kind of like the early iterations of rain on grid models, and how we did this is you actually you kind of clip the embankment break line of your structure and you offset it from the embankment to allow flow to pass through the structure. However, after discussions, we do not recommend to use this methodology. It is often hard to enforce in your model and can allow a lot of flow to pass through the model without creating much headwater upstream of your structure. So moving on to methodologies that we do recommend, the first being V-notch break lines. So a V-notch break line is you take your embankment centerline break line here and you create a little V-notch in it. And typically that V-notch is about the width of your structure, so you can approximate that using aerial or different sources of data. And the third methodology is hydroconnectors. This is where you actually physically modify the underlying terrain of your model and you burn a connection through your embankment. So for either the V-notch break lines or for your hydroconnectors, the end result that the model actually sees is very similar. If you run a profile line across your V-notch break line or the centerline embankment break line, the hydroconnector methodology, you will see a very similar elevation profile. You will see that both those methods basically essentially burn in a V-notch into that embankment, and this is what allows flow to pass through the embankment while also creating a headwater effect upstream of the structure. So moving on, the next few slides here will talk about different ways you can modify your terrain data for hydraulic models. This first slide will talk about bathymetry data. So here's an example of a classic hydroflattened DEM surface, and here's an example of that same DEM with bathymetry data burned into the surface. Whether or not you incorporate bathymetry data depends on level of study. Typically, it's only done for detailed streams. However, depending on the size of the stream, it might be also appropriate for approximate studies as well. But in either case, you need to consider base flow. There's two examples laid out here. The first being if you have incorporated bathymetry into your model and you're modeling a wholly contained or a headwater portion of a watershed, you might want to consider adding base flow back into the system using lateral inflow hydrographs, for example, because a typical rain-on-grid model won't actually model the base flow within your watershed. Conversely, if you do not incorporate bathymetry data and you have inflow hydrographs coming into your model, you might want to consider removing the base flow portion of those inflow hydrographs so as not to double count for that volume within your system. So next I'll touch on building footprints. So if you're modeling in an urban area, you actually can enforce building footprints into your underlying terrain to force flow around buildings. However, I will say the default approach still should be just to increase your Mannington value for buildings for most cases. However, if flow direction matters or flow redirection matters a lot, you can enforce building footprints into your terrain, or for other programs, you can simply just turn off cells to force flow around these areas. I will note that for HECRAS, make sure that you also are enforcing break lines along the walls of the building footprints to ensure that the mesh sees the increased elevation around the building footprints. And also, when you're plotting your final results, the floodplains will not plot through the buildings. So make sure that you are editing the floodplains as appropriate to make sure the floodplains are plotting through the buildings for your final result. So the last topic I'll discuss before giving back over to Jeff is 2D floodways. So I know that the third presentation in this session will discuss 2D floodways in great detail, so I'm not going to go into it too much here. However, I will summarize the recommendations that we made for actually enforcing the 2D floodway, at least into a HECRAS model. So the best way that, or I guess the recommended way that we found was to actually modify the terrain and use that to enforce your floodway encroachment boundaries. So once you determine your 2D floodway boundary, you simply just increase the terrain everywhere outside of that boundary, leaving what's inside the boundary the same, and then running your 100-year flow hydrology through your system to determine your floodway elevations. However, it's not that simple for rain-on-grid models usually. So for most models, you're only going to have a few reaches within your watershed area that have floodways. So for simplicity, for runtimes and iterations of the floodway, you typically clip down the model area to just the reaches with floodways, which removes the rain-on-grid aspect of your model. So in order to make sure that you're still matching your 100-year flows along your floodway reaches, you can establish flow checkpoints and determine the tributary flows to each of those checkpoints and sample from the 100-year run and reintroduce those flows in your floodway run as lateral inflow hydrographs, as shown here. And with that, I'll turn it back over to Jeff.
Our group had a lot of good discussion around model calibration and validation, getting into details that we don't have time for here. But one thing I did want to highlight was that was helpful is to establish kind of a hierarchy of sources in terms of agreeing upon what to give most weight to when calibrating or validating your model. And the first one that we came up with was comparing it to recent events, especially where you can get aerial coverage and compare lateral extents rather than just a fixed point. So an example here shown in this slide is you can see this is an area that you could geolocate because you've got a street sign, you've got the restaurant name, and then you can get an approximate value of depth just by estimating from features in the picture. So you got the trash cans up on the curb, you have this man, it's about almost to his kneecaps in terms of depth. And I'll show you some examples of that later and how that can be compared to your model. The next level of data that would be preferred is gauge data, and specifically if you can replicate a specific event. So if you can get rainfall data from a rain gauge and flow data from a stream gauge for the same event and line those up, then you can get great confidence in your model. If you don't have that, then matching to a gauge rating curve, you can often develop your own, or USGS has a bunch of curves for most of their gauges. And then if that's not available, it's not ideal, but you could try and approximate matching the same return period between rainfall and your flow frequency analysis. We all know that a 100-year rainfall event does not equal a 100-year discharge in the stream, but if that's all you have, it's better than nothing. Continuing on, if you don't have any aerial data or you don't have any gauge data, then the next preferred would be effective data if it's there. And one thing we want to note there is if you have a profile, try and match along the entire profile rather than just at a fixed location like a bridge or a certain crossing. But it can be rather telling to look at your profile in terms of trying to match it compared to just a single point. And often if you calibrate to a gauge but you don't look at the rest of your profile, you may have the whole profile off, mismatching like that. You want to make sure that it's aligned and that the depth or that difference is consistent across your whole model. If you don't have effective data, then there's really not that much left. I would say before you use regression equations, hopefully there's some sort of regional comparison you can do. Maybe there's a gauge drainage nearby and you can use gauge transfer or look at gauged unit discharges at least. But if you don't have anything, then there's regression equations. Now, we would assert to be sure not to calibrate to that, but just to use it as a checkpoint to see if you're within the standard error band within the regression equations, but not to force it to match, because honestly with the technology we have, likely the results we'll be getting if your model was developed well could be better than the regression equations. Last thing I wanted to show here is this table kind of shows what are the different knobs you can turn during calibration. I think most people are familiar with this, but I just wanted to throw it up there. And so you can see as you move further to the right, it has a greater impact on discharge. If you move further down, it has a greater impact on stage. Obviously, your discharge has a direct impact on stage, but the items that are increasing on stage but not so much on discharge are items that don't affect the discharge, but they do affect the stage, whereas pretty much anything that increases your discharge is going to increase your stage as well. So I'll just leave that there for your reference. This slide just shows some quick examples of what I was talking about, that first one in terms of the hierarchy of matching to aerial extent. So here's an image of flooding where you can see it and compare it to the lateral extent. Others would be looking at specific locations within the model that you can geolocate and estimate depths based off of known objects. And then also, if you don't have that, even just newspaper articles that say, you know, there was 14 feet of flooding at whatever street intersection or an underpass, you can look at those locations within your model. And this is something that I'd like to see kind of the engineering practice start embracing, maybe non-traditional sources for model verification. This will be the last technical item we'll be able to showcase here, and I'll have to be way briefer than I would have liked, but this is about 2D mapping, specifically looking at HEC-RAS rendering. There's horizontal and sloping for those that are familiar with it. Horizontal will give the stair-stepping approach, whereas sloping will show more continuous, but sloping often overestimates, particularly where you got steep slopes and hillsides. But this graphic kind of shows that there, and on in these red areas is where, under the horizontal method, it would show dry ground. So obviously this is not an acceptable output. So one thing that our group did is we did a test or a trial where we shared a BLE work area, and we each mapped the output from the same final run to compare it. So on the right here in black is showing the sloping raster, and each of these green dots are the cell centers. This was one output that relied mostly on the sloping, but it pulled in on the edges. Here's another output that used some of the horizontal and then created its own tin from it. And then this was a similar output as well, the blue. But you can see each of these gave a different result using the exact same values. So how you process the results can have a considerable impact on the end product. And if you want something more technicolor, there it is with terrain. Now this is in a fairly flat area by comparison. These differences are highlighted with the stair-stepping approach using the horizontal when we get in the steeper channels. You can see black again is the sloping raster from HEC-RAS. Purple is, or pink is derived from the sloping raster, so it's mostly connected. But then the blue and the green were horizontally based, so you see they're pretty disjointed. So the takeaway from all of this is that there's multiple approaches with considerably different results depending on the terrain and mesh, but each is going to be narrower than RAS sloping render. The horizontally based tools, they perform very well in flat areas, but they break down into steep areas. The sloping base gives more continuity in the steep channels, but all of them are going to require some degree of cleanup, and you have to be beware of overly aggressively automating the cleanup process, and that a lot of these decisions can also be improved by just refinement in your mesh. So to conclude, this presentation really could have been a couple hours. We only barely scratched the surface. We wanted to introduce the overall effort, and then you can reach out to myself if you want more information on it. But really want to say thank you to many engineers who participated in this. I learned a tremendous amount from this. I appreciate Josh joining in on the effort and presenting here, and we look forward to your questions.